In today's video, we will be talking about the motion equations. After watching this video, you should be able to use the kinematic solving techniques that are discussed in this video to solve kinematic problems, and then know and successfully use the various kinematic equations that will be presented in this video. So there's some big-time concepts that are coming up in this lesson, and so it's an important one that you may need to watch more than once, and you may need to come into class with some good questions because it's something that you need to be able to learn and do. So we're going to kind of get into the math piece of kinematics right now. So you may say to yourself, well, why do we even need these equations in the first place? The reason why is equations are a guide to thinking, a way to explain what is happening. Okay, and you can actually put a numerical value on what's going on. So just saying, oh, something's going kind of fast. Well, what does that mean? And typically an equation is a way to kind of explain how fast something is going, where it will be at a certain amount of time, and all that good stuff, right? And there are basically going to be 5 kinematic variables. And I really recommend memorizing these 5 variables because I'm going to recommend that you write them down every time you do a kinematics problem, and it'll be useful for this chapter, and it'll be useful for the next couple chapters actually. So here they are in all their glory right here. These are the 5. Okay, so displacement is 1, the initial velocity and the final velocity is 2 and 3, 4th is the acceleration, and 5th is time. Okay, so those are the big 5 kinematics variables that you really need to be able to, I would just say, learn to list them at any time you need to. Okay, so displacement, initial velocity, final velocity, acceleration, and time. Knowledge of each of these quantities provides basically information about what the object is doing, and so that's why they are important. Okay. The 4 equations that we're going to talk about in the very near future basically work to describe the motion of an object with constant velocity or constant acceleration. The big thing to keep in mind, and we won't see it happen in this course, is if the acceleration is changing, none of these equations will work. At least we won't see it happen right now, I should say. I should back up and say we won't see it happen right now. So if the acceleration is changing, these equations won't work, and so it's no good. So either you have a constant acceleration or you have no acceleration at all. It can't be a middle ground in between them, okay? So before we get into the equations, I just want to quickly clarify what each of the symbols mean. And so if you feel confident with this stuff, just kind of don't worry about it. But if you're worried about remembering the symbols, maybe write this stuff down. D stands for displacement, okay? And sometimes it'll be written as X, basically the same thing. But D stands for displacement, and typically this will be measured in meters. It doesn't have to be, but typically that's what you're going to see it in. Time is T, and typically that's going to be measured in seconds. V stands for velocity. Now with this, there are 2 different types of velocity. There's V sub I, which stands for the initial velocity. Okay, what velocity does the object start with? And V sub F, which stands for final velocity. Well, what is the ending velocity of the object? And don't be afraid to say that it's 0. That is a true possible number that you could put into there. So it could have an initial velocity of 0. So a good example of this would be like if I go on top of the roof and I drop a plastic soda bottle off the top of the roof. When I'm holding it in my hand prior to dropping it, what is the initial velocity of that soda bottle? It's 0. Okay, so that's perfectly fine to say. The acceleration is represented by A. Okay, and if you're doing a free fall problem, now not every problem is a free fall problem, but if the only acceleration is the force of gravity, well, we know that would be 9.8 meters per second squared. So G equals 9.8 meters per second squared. Now this is only true in free fall problems. That's not the only type of kinematics problem that we'll see. Okay, so let's get right into the equations. Okay, so let me change pen colors here. So I am not writing in red with red text. So this is the first one, and there's really no order to it. You could call it the fourth one if you want, but the first one says distance equals v initial, which is the initial velocity, times, that's what that stands for, times time plus 1/2 times a times t squared. So d equals v sub I times t plus 1/2 at squared. That's the first one. The second one is v sub f, or v final squared, equals v sub I, or v initial squared, plus 2 times the acceleration times the distance, or the displacement, I should really say. So that's the second one. The third one is v sub f, or the final velocity, equals the initial velocity plus the acceleration times time. So this star thing means multiply. Okay, just in case you're confused. It looks a little crummy on my screen right now, so it probably doesn't look real good at home. And the final one, the fourth equation, is d equals v sub I, or initial velocity, plus v sub f, or final velocity, divided by 2, and really I suppose this should be in parentheses, times time. Okay, and I'll be honest with you, when I was taking physics, I wrote this stuff down on the front of a folder, and so I could refer to it very easily. These equations you'll use over and over again for the next probably couple of weeks, and so I would have it in a place that you can quickly look at them. I don't expect you to memorize these. You can use a note card on the test, and so these would be things I probably would write on my note card, to be quite honest with you. But I would have these down in a place that you can refer to them relatively easily. You'd be surprised. In a couple weeks, you might actually start to memorize these things because you use them so much. All right. This slide looks massive, doesn't it? But these are basically the equation solving strategies. And I know sometimes this may seem a little bit tedious or time consuming to do this for every single equation, but until you get a firm grasp on what you're doing, in physics, if you follow this kind of like flow chart, if you will, on what you should do, it really helps to eliminate error. Okay, so I highly recommend you follow these strategies. Obviously, you can do whatever it is you want in terms of solving problems, but I think this is a good step-by-step method to go about solving kinematics problems. So the first thing you do is you construct a diagram of the physical situation. I love pictures. It really helps to be able to see what's happening. So I highly recommend you draw a picture. On your picture, I recommend labeling the initial and final position. So where's like the starting position and where's the stopping position? After you've made a picture, I also recommend, and I wish I would have written this in there, locating the positive and negative axis. Okay, locating positive and negative axis. One of the big places where students will make mistakes, this is plus and, that's an and sign, sorry about that, and negative axis. One of the places students make mistakes is just forgetting signs. Okay, and so putting the signs down is really big, which actually is a step later on. Then you write down the 5 kinematics variables, which was mentioned, I believe, like 2 slides ago. So the 5 kinematics variables, again, is v final, or the velocity final, the initial velocity, or v sub I, time, acceleration, and displacement. Those are the 5. All right, and I just recommend writing those down right underneath your picture. Then, after you've written those down, you write down the value for each variable that's given to you in the problem and include the sign. This, like I said, this is where a lot of people make mistakes because they forget the negative sign or they forget the positive sign or whatever. So you write the value down, and I actually recommend writing plus in front of the numbers because then it's helping you remember to keep the signs straight. Identify the variable in the question with a question mark that they want you to solve. Okay, and that sounds confusing right now, but if they're looking for, say, like displacement, underneath your displacement variable, I write a big old question mark because that's what I want to find out. Okay, that's the thing I'm wondering about. Then you pick an equation to use, so one of the 4 from the previous slide, solve for the unknown information, and then check your answer to make sure it makes sense. Okay, so like if you're saying like a dude threw a football 900 meters per second, that's the velocity of the football. Well, no one can throw a football that fast, so that probably isn't quite right. So make sure your answers make sense. So if you say like the height of a cliff is 3 centimeters, well, that's like, like maybe the length of your fingertip a little bit or something like that. So it's like that doesn't make sense. What kind of cliff is the size of a finger? So checking your answer is a really good idea also. On the front of the classroom board, you'll notice something called dude, and that basically is a synopsis of what I just mentioned in the previous slide. I can't fit all that on the front board. So when you're not doing something correctly, I'm probably going to dude you. And basically what that means is this is a method, a quicker, shorter method of solving problems in physics. And dude stands for it's a mnemonic device. D is draw the problem. U is uncover knowns and unknowns. So write them down, dang it. Decide on a formula. That's D, the second D. Decide on a formula. And E is execute algebra. Dude. Okay, so I think it's maybe a little easier way to remember it, but the previous slide is really a nice step-by-step method in terms of solving problems. And in the two examples I do in this video, you can kind of see me go through those steps in just a second. Okay, so here we go, an example problem right now. It says, Ben is waiting at a stoplight. When it finally turns green, Ben accelerated from rest at a rate of 6.0 meters per second squared for a time of 4.1 seconds. Determine the displacement of Ben's car during this time period. Okay, so we're looking for the displacement of Ben's car. Okay, so one of the first things I want to do is I want to draw a picture. Okay, and if you, I'm going to change colors. That does not show up well. Let's do magenta. Here's Ben's car. Okay, and this is where it's starting. Okay, and it's going to move some distance and then it's going to stop. Now, if you don't want to do all this drawing of a car, you could easily just do a dot, okay, and another dot, start, stop. Okay, that's a pretty simple picture of what's going on. Because all these numbers in here do not have a negative sign in front of it, I'm going to just assume it's moving to the right or in the positive direction. So I just quickly draw my two axes. Right is positive, up is positive, okay, and everything else is negative. And it looks like everything's going to be positive in this problem because there's basically no number that indicates it would be going like to the left or anything like that. After I've done all that, after I've drawn all my pictures, I'm going to write the 5 kinematics variables down. And those are V sub F, V sub I, T, D, and A. And I'm just going to draw some lines to kind of divide them because I put these pretty close. I just don't want to run out of space here. Okay, so there they are. There's the 5 kinematics variables. You basically need to know 3 of these to be able to use one of the equations that we talked about. So what do I know in this problem? Well, as I read through the problem, it says Ben accelerated from rest. Okay, anytime you see that, that is an indication that it's starting at 0 meters per second. The initial velocity is 0 meters per second. And that's sometimes what makes physics tricky, is that they don't just come straight out and tell you that, oh, the initial velocity is 0. You have to use your noggin to figure that out. So the initial velocity here is 0 meters per second. So Ben accelerated from rest at a rate of 6.0 meters per second squared. So he is accelerating at positive 6 meters per second squared. Notice how I put the sign down here of positive. Okay, I know it's annoying maybe to write positive, but I think it's a really good habit to get into. Okay, for a time of 4.1 seconds. Now, time is always going to be positive. You never have a negative time. So if there was going to be one that you were going to skip putting the sign down on, time is it. Okay, so I don't believe you have to put a sign on. If you want to put positive, you can. It's not going to hurt your answer, but you'll never have a negative time. Okay. Determine the displacement of Ben's car during this period. So we're looking for displacement, and this is where you write that big question mark down. That's what I want to know, is what is the displacement of Ben's car. Okay. So I'm not going to even worry about V final right now. Okay, I have no information about it. They aren't asking me about what's the final velocity, so I'm not going to even use it. So then I look at my list of equations and I find one that looks like it might be useful. Okay, and the one I'm liking a lot is D equals V sub I plus 1/2 AT squared. Right. And you notice I didn't put the little multiply sign between all these things. If you don't want to do that, be my guest. You don't have to do that. Okay. So here we go. We have our equation, and now I just look at my numbers and I plug them in. So what is my initial velocity? My initial velocity is 0 plus 1/2. 1/2 is just 1/2 times the acceleration, which is positive 6 meters per second squared, times time, 4.1 seconds, and this is squared, and that's going to give me my d. What is my displacement? Well, if you throw that into your calculator, and I'll just kind of trust you to try to do that, I get an answer of 50.4 meters. That would be my displacement, or I should say Ben's displacement. Now you can see these problems take some time, and that really is, there's really no shortcut or fast way to solve these problems. So sometimes it's just, kind of got to grin and bear it, and you sit down and you actually do all this work. And if you do that, the reward is usually you have the right answer. Sadly, there is no shortcut. For problems dealing with free fall, so if you remember the previous lesson, we talked about free fall. Just some hints, things that kind of can help you solve some problems. When objects are falling down, they have a negative acceleration. So A is negative. Okay, so down is going to be negative. If an object is dropped, so if I say like I drop a bottle off the top of the roof, its initial velocity is 0. So that's a big hint. Like if they say I'm going to drop an object off the Empire State Building, the initial velocity is 0. They won't straight out tell you v sub I is 0. If an object is thrown upwards in a perfectly vertical direction, it will slow down as it rises upward. The reason why it slows down is because gravity is pulling it back down to the earth. So I mean, you can go outside and try it today if you want. Throw a golf ball up into the air. It'll fly up, but as it flies up, it starts to slow down until eventually it hits a peak. At that peak, its velocity is 0 meters per second. The velocity is 0 meters per second. So for just an instant, it's in the air and it stops. It's not moving at all. It's actually changing directions. So that's a big hint that you can kind of cut free fall problems in half and look at the peak. So from the point where you threw it to the peak height, that can be like part of the problem that you look at. So at the peak, the velocity is 0 meters per second. If an object is thrown perfectly vertical upwards, then the velocity is the same as the height on the way down. That sounds really confusing, but this example might help. If you throw a ball upwards at 20 meters per second, it will come down at 20 meters per second once it reaches the height of your arm or whatever it was that threw it. So if I launch a cannonball up at like 100 meters per second, when that cannonball passes me going down, it will be going down at 100 meters per second. Okay, there's some symmetry to these free fall problems. Okay. There's some hints to keep in mind as you're solving problems. Let's do one example problem and then we'll call it a day. Rex throws his mother's crystal vase vertically upward. What a jerk. With an initial velocity of 26.2 meters per second. Determine the height which the vase will rise above its initial height. Okay. So one of the first things I do is I want to draw the problem. Okay. And I wish I was a better artist. I really do. But here's Rex, and I'm just going to make the vase be a dot because I'm not even going to try. Okay, this is the starting position. Okay, and he throws it up. All right, and they want to know at which height will the vase rise above its initial height. Okay, so what's the peak, if you will? So it will stop here. Okay, so he throws his vase up, and when does it stop? Okay, what is this height? All right, so maybe I'll draw a little like doodad here. We are looking for the displacement. Okay, that's another way of saying it. What is the displacement? Okay, and your picture can include whatever you want, and that's why I love pictures. I think it really kind of helps see what's going on. Okay, so I drew a picture. I'm going to label my positive and negative axes. So positive is up and to the right. And if you want, we can do the negative. Negative is down and to the left. Okay. So here we go. We have a good start, right? So I've drawn a picture. I've labeled my starting point, my stopping point. I've labeled positive and negative. Now I'm going to write down the 5 kinematics variables. And those 5 variables are v sub f, v sub I, t, a, and d. And I did a better job of spacing them out this time, except my d looks really funky. All right, so what do I know? Maybe I'll change pen colors just to kind of make it a little bit more exciting. Let's do yellow. So V final, well, let's just read through the problem first. Rex throws his mother's crystal vase vertically upward with an initial velocity of 26.2 meters. All right, so this time they tell me the initial velocity is 26.2 meters and it's going up. So what is the sign convention of up? It is positive. So this is a positive 26.2 meters per second. Determine the height to which the vase will rise above its initial height. Okay, so I don't know much else, right? Well, let's think about that for a second. In just the previous slide, I'd given you guys a hint when you have free fall problems. And that's really what this is. After Rex throws his vase up in the air, what force is acting on the vase? The only force left that's acting on the vase is gravity, okay? Because remember, we ignore air resistance. So when this vase gets to the top, what is the final velocity? The answer is 0. All right, believe it or not, it stops for just a second and there's no movement. So it actually is 0 meters per second for the final velocity. Okay, so we actually know that. Even though it doesn't come straight out and say that, we can interpret that either from our diagram or just from using our noggin. Okay. In terms of time, it doesn't look like they give me much information on that. Now, what is the acceleration of this vase? Once again, they don't come straight out and tell us the acceleration. We just need to realize that what is the only force acting on this vase? The only force acting on this vase is gravity. And what is the acceleration due to gravity on Earth? Well, it is negative 9.8 meters per second squared. Okay. Why is it negative? Because gravity always points down. It's always going to pull stuff down. So gravity will be negative in this case. Okay. So if you remember, in the previous exam problem, I said you only need 3 of the 5 kinematic variables to solve any problem. And so do I have 3? I do. Okay. So the question is, what is the height that the vase will rise above Rex's initial starting position? And so we're looking for displacement. So I put a big question mark there, right? What is the displacement? I'm going to change colors once again just to kind of, I don't know, keep things exciting. So now that I've done that and I've inserted the values, I've marked with a question, I want to decide on a formula. The formula I'm thinking I will want to use is this one. V sub F. Oh, I've used this color already. Gosh darn it. See, I've used yellow. I'm trying to think of ones that come out well. All right, can I fix this? Maybe. V sub F squared, I'm really sorry. V sub F squared equals V sub I squared plus 2AD. Now notice I didn't put the multiplying signs here. To me anyway, it seems to get more like messy and I don't like it. But if you like the multiplying signs, put them in. You know, you do what you need to do to make things good. Okay? So now that I have an equation down, I can start to plug numbers in. So what is my V final? My V final is 0, right? So this just becomes 0 equals V initial, which is 26.2, and I forgot to put the positive sign. I will do this often, and that's squared, plus 2 times, what's the acceleration? It is negative 9.8 meters per second squared times d. Okay? So this is where you really have to have your algebra skills down pat because you need to get d by itself. So you're going to take 26.2 squared and move it over to the left, okay, and you're going to have some value there. And then you divide that value by 2 times negative 9.8 meters per second squared. And if you do all that, so this is just making the assumption that you guys will be able to do the math piece to this. Let me see if I can get a different color for my answer to make this more exciting. Let's do green. The d, or the displacement, would equal 35.0 meters. Okay? And I do that a lot in my videos. I just kind of do the assumption that you'll do the math with a calculator and kind of check to see if you're getting the same answer as me. If you aren't getting 35 meters, you can come and see me in class if you want, or just try it again and see if you can get it. But you should get 35 meters as the displacement. That takes care of this video. I will see you guys next time.